Okay, welcome back. Today we're going to be talking about optimization, which is an application of derivatives when you're trying to, as the title of the chapter says, optimization. Simply put, this is just word problems. Like it's actually not more complex than that. Let me turn off that microphone. Yeah. It's just word problems with using derivatives, but of a style that you've probably seen before. So maybe in high school, in algebra, you saw questions like find two numbers, x and y, that when added together equal 62 and then like multiplied together equal, I don't know, let me get my calculator out. Let's say it's 62 minus 12, 50 times 12, and multiply together equals 600. And so it would essentially look like that, and then what you would do would be, okay, I'll just solve it like a systems of equations, where we have x equals 62 minus y, and then we plug that in the other one, and we get 62y minus y squared equals 600, and then it's divide by 62, I guess. Let's see if 600 is divisible by 62. Nope. But it would work more or less. So we get y 600, 0 is going to be equal to y squared minus 62y plus 600, and then you would factor it. Probably use a quadratic form equation. So let's see, negative b plus or minus the square root of b squared, which would be 62 squared. 3844 minus 4ac minus 4 times 600. Yeah. So inside this, you would end up with 1444, and then that would all be over 2a, which would be 2. So the square root of 1444 is going to end up being 38, so it'd be 62 plus or minus 38 over 2. And then we would end up, that would be what y is. Y equals 62 and 38. So 62 minus 38 would be 24 over 2, would be 12. Or it could be 50. And coincidentally, the numbers I chose were 12 and 50. And now we have our answers. X can be 12 or 50, and y can be 12. It just has to be one or the other. And that would satisfy the system. But let's add another element into it. The question is no longer find a value where it's equal to this. Find a value where the product of the two is a minimum or maximum, whichever one you want. So now it's not just find a number. This number has been removed from the equation. And it just says, whatever that number is, we want it to be the smallest possible, or the biggest possible. So let's do the smallest. I'm going to replace this with a negative, just make it easier. And xy is going to be equal to min. We don't know what that minimum is. So how do we do this? Well, derivatives tell us where changes happen and the change in a function. So what we can do is we can actually just find the derivative of one of these with only one variable, and then solve for x, because that will tell us when the derivative crosses 0, that means that there is a minimum or a maximum at that point. So let's go. So we're going to start off the same. It'll be x equals 62 minus y. Then we substitute that into the other equation. So it'll be 62y squared, or 62y minus y squared, equals minimum. But we don't actually know what the minimum is. uh, but we don't need to because this is a function. So min of y, or f of y equals that. And we just have to take the derivative. So we'll get 62 minus y equals 0. I think. No, something's wrong. I see my problem. It's plus y. So 62. Heh. Where did we go wrong? I did this correctly a minute ago. We'll look at the worksheet. It was difference is 62, so x minus y equals 62. And product is a minimum, so x equals 62 plus y. And substitute that in for xy, so y is 62y squared plus y squared equals a minimum. Heh. Oh yeah, okay, here's my problem. Just apply the power rule incorrectly. So 2y, 62 plus 2y is going to get us what we want. Is going to be equal to 0, so 62 equals negative 2y, and negative 31 is equal to y. Boom. So that is where our minimum is. Now, what we can do is plug it back into the other equation. So x minus negative 31 equals 62, which means x plus 31 equals 62, and therefore x equals 31. Boom. And it's as simple as that. It's just another step. It goes beyond find a value. It's find the smallest possible value. And if you plug in, or if you put it on a graph, you will find that 31 and negative 31 are the two numbers that will result in this thing. So let's make it a little harder, because that was a really simple question, except for the fact that I messed up the derivative. All right, let's look at the examples. Okay. Consider the following. A box with an open top is to be constructed from a square piece of cardboard, which means we have a square piece of cardboard, which is 3 feet wide, and we're going to do this. Oh, it's a square, so it's going to be like that. Okay. Square piece of cardboard, 3 feet wide, by cutting out a square from each of the 4 corners and bending up the sides. So we'll just cut out the corners. Oh yeah. And so find the largest volume that such a box can have. So what are going to be the dimensions? It will look like this. I'm going to draw a cube so we can see what the final box would be like. So if we want the box to be the largest it's going to be, we know that this side right here is going to be the side length. So I'm going to say y is a side length. So y and y right there. X is going to be the base length. It's going to be that and that. So we have x and we have x. So the base is going to be... Wait, does it have to be though? That's the question. What is it wanting? Cutting out a square from each corner. Yeah, so if it was a square on each corner, then it would end up that these have to be equal. This is equal to this. Because if you have a square and then you square, 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 like the only possibility is that this is equal to this. And then these little bad boys are all y. So the volume of our box is going to be equal to x squared y. Now it's asking, Find the largest volume that such a box can have and draw several diagrams to illustrate the situation. Okay, so we need another equation to fit into our system of equations to figure this out, which is going to be this. We know that the area of it is going to be 9. And how do we calculate the area? Well, let's look at this. If this is going to be y, the length of the little square, then 2y plus x is going to be equal to 9. 2y plus x squared is going to equal 9. Easy. Yes. Double check that. So we have y, and then this is x, and that's the base, and these are the sides. So the length of the side is going to be 2y. Okay. And we can even do it with a side length. We could say 2y and plus x is going to be equal to 3, which would essentially be the same as the area because it's a square and take the square root. So let's solve. Now that we have our system, let's put them together. So x is going to be equal to 3 minus 2y. Draw a line there. X is going to be equal to 3 minus 2y. So 3 minus 2y squared times y is going to be equal to our volume. Now all we have to do is, well, I would simplify this first just to make it easier. 9 minus 6y plus 4y squared. All of that times y, so 9y minus 6 plus 4y cubed equals volume. This makes sense because volume is going to be a cubic thing. So now we take the derivative, 9 minus 12y plus 12y squared, going to be equal to, for where it crosses, so it's going to be equal to 0. So now let's solve. I'm going to rearrange this so it looks simpler. 12y squared minus 12y plus 9. We can factor out a 3, and we can get 4y squared minus 4y plus 3. And let's continue on with the factoring. So it'll be a 4y and then y. I believe this will be plus y plus 1. Okay, so then this would be a minus and this would be a plus. So let's check it. 4y squared. And then the 4y. Oh, these would both have to be negative. Oh, what's going on? Apparently don't know how to factor. So 4y squared minus 4y minus 3y. Ooh, 7y. And then we do get the plus 3 at the end, so that's incorrect. Let's go to the calculator and see what happens. 4x squared oh, it appears there are no zeros. How do we confront this? I'm going to pause it real quick. Oh yeah, I found my error, which is that I did not take the derivative. Man, I'm really tripping today. So, erase this. We can simplify it, which would be 12y squared minus 12. Wait, that's not the problem. Okay, I'm going to start over. Okay, I found my error. More algebra. This is not a 6, this is going to be a 12, so minus 12y. That's why you should always do your math by hand, guys. That's going to be 12, which is going to end up with 24. Alright, let's continue on. Anyways, we got 12y squared minus 24y plus 9. So now we can take out 3, and we're going to get 4y squared minus 8y plus 3 equals 0. Yep. So this makes it a little easier. We can do 4 and 2. Okay, so do some quick factoring. So I think it would be 4y minus 3. Nope, it would be 2y minus 3 and 2y minus 1. So let's see if this gets it right. So 2y squared, or 4y squared minus 2y minus 6y is going to be negative 8y, and then that's going to be 3. Okay, so now with this set equal to 0, we can solve y equals 3 over 2 and y equals 1 over 2. Okay, it looks like we have two potential values for what our ideal value of y is going to be. So what do we do? Well, we can plug it in, and we can solve for x. Let's go back to the original. 2y plus x equals 3. 3 over 2. So 3 plus x, we go to 3, which means x would be 0, which means that this is not going to be a solution. And we can do the other one, or we can say 2 times 1 over 2 plus x equals 3, and that would be 1 plus x equals 3, which will get us x equals 2. So let's plug that into our equation, where y equals 1/2. So 1/2 and x equals 2 squared. So 4 times 1/2 is going to be 2, which is equal to our volume. So that means the smallest volume that we can have is going to be 2. And that's exactly what it is, 2 feet cubed. So I'll call your attention back to here with our zeros. So we ended up getting 2 zeros. And why is this? Because the smallest volume a box can have that's like this is actually 0. Like, it can have no volume, which would be where there's technically a height where there's no width or length. It's just a single length. It's in a different dimension. So we have to plug both of them in and see which one works. Now, if the final answer ended up giving us a cubic box, both of our values would have been solutions because all the side lengths would have been the same. But in this case, it wasn't. So we ended up with two different values where only one of them was valid. So that works. And let's continue on. Okay, here's a tough one that took me a bit the first time I solved it. Okay, a rectangular storage container without a lid is have a volume of 10 meters cubed. So let's draw our storage container. I'm tired of blue. Let's go to black. Okay, rectangular storage container volume equals 10 meters cubed. The length of its base is twice the width. So if this is length and this is width, we can say the width is x, the length is 2x. And material for the base costs that and that. And it wants to know material for the sides costs $9 per square meter, and define the cost in dollars of materials for the least expensive of such container. So what we need to do is figure out what y is going to be, which is the height of the container, to have the smallest surface area. Because we're going to be measuring surface area, because that's how we determine what our price is going to be. So if 2x squared, which is going to be length with height, so length with height is equal to volume, so 2x squared y equals 10, and surface area, which is going to be base times base, or the length times width, 2x squared plus, and this is going to, plus the sides, is going to equal to surface area. So let's plug it in. So for this side and the other one, it's going to be xy, so 2xy, plus 2x times y is going to be this side, and then 2 for that, so it's going to be 4xy. And then that's going to get us our surface area. So let's double check. This is the base, single base. This is width times height, and this is length times height, times 2 times 2. So width xy times 2, 2xy, and then 2x times y. So 2xy times 2, it's going to be 4xy. So we're good. So now we have our system of equations. And we're going to solve to figure out what the lowest possible value is going to be. So let's figure out from here. This looks like the simpler one for what we need. First step is to solve for x and y. So I'm just going to say y equals 2x, y equals 10 over 2x squared, which is equal to 5 over x squared, because 10 over 2 is 5. So now that we have that, y is going to be equal to, or our second equation can be substituted with 2x squared plus 2x 5 over x squared plus 4x y is going to be 5 over x squared. That's going to be our surface area. So let's simplify it down. 2x squared plus 2 times 5 is going to be 10x over x squared is just going to be 10 over x, plus 4x times 5 is going to be 20x over x squared, which is going to be just 20 over x, equals surface area. Now, we can combine these to be 2x squared plus 30 over x is equal to surface area. And to go even further, we can just have 2x cubed over x plus 30 over x equals 2x squared plus 30, or 2x cubed, sorry, over x equals surface area. Now we're going to want to find the derivative to find where that can have its smallest possible value. Might have overcomplicated that. Let's actually use this. So cross out the simplification. We're going to take the derivative of this one. 4x, is that correct? Yes, 4x plus, and this is like 30x to the negative 1. So it's going to be negative 30 x to the negative 2, negative 30 over x squared. So minus x squared equals 0, because that was a derivative. Erase this. Oh, I got a message. Okay, not important. So now we have to do is solve for 0. So what we can do is we can multiply by x squared, and everything will be fine. So we'll get 4x cubed minus 30 equals 0. And so 4x cubed is going to be equal to 30. 30 over 4 is going to be 15 over 2 equals x cubed. So all we need is the cube root of 15 over 2. X equals cube root 15 over 2. Now, this looks like a really weird number for now, but the final answer is not dependent on what this number is. It is, but it's actually the price, which is going to be a rounded number, so we don't have to worry about being extra precise. So we can stay here and be comfortable that x is the cube root of 15 over 2, even though that feels like it's going to be a really weird number, which to me rings some alarm bells, but we don't have to worry too much about it for now, because if I remember correctly, it's that way. Hi. Do you need this room?
No, not right now.
Okay.
Would it bother you if you stayed here?
I mean,
Yeah,
no.
we're about to take a test in 20 minutes.
Y'all
In this
are?
classroom. Yeah,
In this classroom?
Yeah, this is a teaching class.
Okay, I'll
But
head
you're
out then.
good for till
No, I'm like
1:15?
giving a lecture essentially, so I would probably bother y'all.
Sorry.
Yeah.